Hi, I'm Emanuele Caimi from Desme Ballestra, Italy. Today I will talk about the technologies and trends related to the minimization of dioxin content in ethoxysulfates. But before starting, let me thank ICIS and Neil Burns for the opportunity to connect with all of you, even if remotely. I hope we will have soon the chance to personally meet at ICIS conferences in future. But without any further ado, let's go to the topic. 1,4-dioxane is the main character of my presentation. It is a cyclic molecule, a dimer of ethylene oxide, and a volatile liquid at atmospheric conditions. It is soluble in water and in several other solvents. Industrially, dioxane is produced through the dehydration and re-enclosure of the ethylene glycol, which in turn comes from the hydrolysis of ethylene oxide using sulfuric acid as catalyst. In sulfation process, something similar happens. The formation of 1,4-dioxane is the result of an acidic cleavage of the ethylene oxide chain condensated into the molecule of alkoxylated alcohol. And it happens when the molecule undergoes reaction with gaseous SO3 or with any other sulfating agent with electrophilic behavior. It could be sulfuric acid, oleum, chlorosulfonic acid, or sulfamic acid. Clearly, the purity and the characteristics of the reactants are really the key parameters to control the 1,4-dioxane formation, though the most important parameter affecting the side reaction is the mole ratio between SO3 and organic substrate. Anyhow, even when this parameter is perfectly set for the sulfation reaction, it is still unavoidable to obtain the undesired formation of 1,4-dioxane, although at a limited extent. Another important parameter affecting dioxane production is moisture, which can be due to its content in the ethoxylated alcohol or in the process air, which is used as carrier for SO3. So why dioxane is so scaring for the surfactants industry, especially in recent times? Well, the answer is unfortunately incomplete. Nevertheless, what we know from several scientific studies is that dioxane is considered responsible for effects on human health and on the environment. Even if relatively few data are available, it is sufficiently clear that liver and kidneys are targets of dioxane toxicity. As far as environment is concerned, dioxane is relatively resistant to biodegradation, and the increased concentration in groundwater, especially in densely populated areas, triggered the attention of the legislators. Relatively few studies have evaluated biological degradation of 1,4-dioxane. Typically, indigenous microorganisms cannot degrade the molecule. However, recent studies prove that selected culture of a Mycobacterium or of Rhodococcus can degrade dioxane, even if not always completely and generally at low rates. As well, a potential for anaerobic degradation of 1,4-dioxane also exists. These studies overall suggest that there are some dioxane degraders in nature, and maybe they are more widespread than commonly thought. So, a better understanding of these organisms and of the biochemistry of 1,4-dioxane biodegradation may lead in future to some treatment options for this pollutant. The recorded increase of 1,4-dioxane in New York's water systems is the background to the legislation approved in March 19 by New York State that drastically reduces the allowed content of dioxane in cleansing, cosmetic and personal care products. Basically, starting from January 2023, dioxane content in consumer products shall be limited to 2 parts per million and then to 1 part per million from January 2024. Considering an average ethoxysulfate content of 15% in these products, the maximum allowable content of dioxane in the surfactant referred to 100% active matter basis shall not exceed 5 to maximum 7 parts per million. Now, we have to come back for a while to the physical characteristics of dioxane and especially its interaction with water. In fact, at standard conditions, dioxane provides an azeotropic mixture in water, roughly having ratio 80 to 20 in weight and boiling at around 27 Celsius degrees. This property allows to separate quite selectively the azeotrope, exploiting the difference in boiling point with water. Dioxane can be therefore stripped off and then condensed. So the azeotrope of dioxane in water is the key for ethoxysulfate purification, but of course is not the only available tool. First of all, any action aimed to limit the side reaction generating dioxane are welcome, like those mentioned here in items 1, 2, and 3. First of all, the purity and the characteristics of the reactants, as said, gaseous SO3 but especially ethoxylated alcohol, are key parameters to control the dioxane formation. Not only, but additionally, a careful setup of the sulfation parameters, and in particular of the ratio between SO3 and organic raw material, are essential to limit dioxane production. And finally, a proper design of the process equipment, minimizing the shelf life of the product in acidic form, definitely has a good impact on the product quality. But unfortunately, all of these optimizations are not enough to achieve the targeted maximum content of 5 parts per million in ethoxysulfate paste. So this is the reason why the SME Ballestra developed the so-called ultra-low dioxane system. It is based on a double-step process, where dioxane is stripped off by different driving forces. The first step consists in the well-known vacuum neutralization, where water evaporation is promoted by the heat of neutralization thanks to the exothermic reaction. The second step, on the contrary, is based purely on a stripping unit, driven by paste heating, and designed in a way to preserve the product quality. And between the two steps, a fine-tuned dilution system allows to keep the right paste concentration. Vacuum neutralization is based on the use of a wide film neutralizer, where acid and neutralizing agent, typically a solution of caustic soda, are fed from the top of the machine at controlled rates. The machine clearly is operated under vacuum and allows to intimately mix the chemicals and at the same time to use the heat of reaction to evaporate dioxane and water. Vapors are extracted from the bottom of the neutralizer and processed in a condenser for their recovery, while the neutralized paste is delivered to the inline dilution step. Compared to the traditional neutralization loop, this system has several advantages. First of all, it is a once-through process. It does not require a circulation loop filling and enables immediate startup or shutdown according to the process needs, and allows even inline product changeover with minimum cross-contamination. The product is directly produced at 70% concentration, so allowing an efficient deaeration and dioxane stripping. But most of all, the unit allows to strip off around 70% of the infed dioxane with very limited or even no consumption at all of energy. Once the paste coming from the vacuum neutralization is added with a controlled amount of dilution water, it can be fed to the second step of the treatment. Here, the water added in the dilution step contributes for further evaporation of the azeotropic mixture. The stripping unit, operating under moderate circulation, allows setting stable and homogeneous conditions, avoiding any peak of temperature that could affect product quality. Operating conditions, generally speaking, are mild. The stripping occurs in a specifically designed flash chamber, again operated under vacuum. The vapors are collected together with those extracted from the vacuum neutralizer for their condensation. The unit is simple, easy to operate, efficient, flexible, and cheap. Alone, it allows a dioxane removal of 50 to 60%, but when it's coupled with the vacuum neutralizer, can achieve an overall efficiency of 90% and even more. Here, two different cases are shown. The first one refers to an inlet of dioxane content of 50 parts per million, while the second one of 30. Both cases foresee to reach 5 ppm of dioxane refer to 100% active metal bases, which are equivalent to around 3.5 parts per million on the paste as is. The overall efficiency of removal is of 90% in the first case and 83% in the second case. Please give a look to the last line, showing the steam consumption in the two cases. Here, two considerations are needed. The first one is that the optimization of the sulfation parameters, whose result is shown in case 2, where we have a lower inlet content of dioxane, has significant impact on the energy balance. The second consideration is that, in any case, the energy consumption is worth a half of the energy used by a pure stripping process to obtain the same results. Before coming to the conclusions, I spend a few words to highlight that the technology to minimize dioxin in ethoxysulfates shall be followed by suitable treatments to destroy dioxin in effluent waters. At present, different options are proven to be technically feasible, including advanced oxidation, adsorption, bioremediation, and metabolic or co-metabolic degradation. Among them, advanced oxidation, using a combination of ozone and hydrogen peroxide as oxidizing agents, is the only industrially viable option. Given the typical size of these units, a PSA system allows to obtain oxygen from ambient air. Oxygen is then used for ozone production, which is put in contact with the polluted water. Hydrogen peroxide is also added to the medium, enabling the production of hydroxyl radicals, whose reactivity allows to break the dioxin ring and start the chain oxidation. Depending upon the pollutant's concentration in a water stream to be processed, different control steps are generally foreseen. So we come to some conclusion. First of all, the control and minimization of 1,4-dioxane content in ethoxysulfates is a must already for US producers, and reasonably is going to become a must also for European and Far East producers in the next years. Secondly, ethoxysulfates are largely used in all the fields of cleanser, personal care, and cosmetic products. They show good performances and they are largely available at affordable price. Additionally, they are bio-based, which is an advantage compared to several potential substitutes like AOS that come from fossil sources. Moreover, solving the problem instead of simply finding a replacement will focus the producers, but of course also the consumers' attention on the effects that their consumption has on health and environment, contributing to developing a higher social consciousness. And coming to more technical items, the possibility to keep using ethoxysulfates, even matching more restrictive legal requirements, has several advantages. First of all, a reduced need of industrial investments. Only some modification or addition are requested to retrofit the existing equipment plants. And moreover, these modifications are achievable in a time frame which is compliant with the laws. Moreover, no disruptive changes in the current supply chain are required. In fact, these changes could affect raw materials availability and product pricing policy. No need of product reformulation, which is, we know, costly and time-consuming. And moreover, all of this is achieved with minimum increase of the operating costs due to the ease of neutralization, which is given by nature to promote 1,4-dioxane evaporation. Some references to works published by agencies and institutions are reported in this slide for further reading on the subject. So thank you for your attention, and feel free to reach me out for any question or comment.